Hi, computers are amazing. There are many types of them. This is a mechanical computer. This is an electronic computer that is not binary. This is a binary computer that made out of dominoes. And these are totally different and weird looking computers. But the computers that we usually see around us are all binary and electronic. Binary means they all use only zeros and ones. And electronic means that those zeros and ones are represented with electrical signals. You may have already heard that computers work with zeros and ones. But how? How the computer with only zeros and ones can understand commands and codes and can create programs that let you stop bullets with your hand? The answer is they have logic gates. Logic gates are the most basic part of all modern computers. There are three main types of logic gates. This is a NOT gate. It has one input and one output. The only thing it does is to reverse the signal. If you apply 1 to its input, its output will be 0 and vice versa. How do you make a NOT gate? Well, this is one way to do it. This design uses 4 BJT transistors. It's a pretty complicated circuit, but we don't have to worry about how it works. All we have to know is that it has one input, one output, and the output is the reverse of the input. Next, we have the OR gate. This is also made out of a complicated circuit of resistors and transistors, but we just know it by this symbol. It has one output and at least 2 inputs. Here I named them A and B, but this gate can have 3 or more inputs as well. Let's add another input and call it C. Okay, now let's use a metaphor to see how the OR gate works. Imagine you're in an elevator with 3 other people. You don't have your watch or phone with you, but you want to know the time. You decide to ask the time and say, "Excuse me, anybody know what time is it?" The other 3 people are nice, and if any of them have a watch or phone with them, they'll tell you the time. But if all of them don't have any watch or phone, then they can't tell you the time. Same for the OR gate. If A is 1, B and C are 0, the output will be 1. If A is 0, B and C are 1, the output is also 1. But if all of the inputs are 0, then the output will also be 0. This is how we write it down. It looks like a simple addition, but it's not. We read it A or B or C are 0. But for this example, the answer is 1, not 2. Here, both B and C are 1. It's like 2 of the people in the elevator have watch and they both can tell you the time, which doesn't matter. As long as at least one of them can tell you the time, you will know the time. Finally, there is the AND gate. Like the OR gate, AND gate is also made out of a complicated circuit of resistors and transistors, and we know it by this symbol. It also has one output and at least 2 inputs. But of course it can have 3 or more inputs as well. AND gate works like a unanimous vote. A unanimous vote can only be achieved if everyone involved agree with the motion. If even one person disagrees, then the motion will not be passed. Similarly, the AND gate is only 1 if all of its inputs are 1. If even one input is 0, then the AND gate will be 0. The way we write AND gate is like this. We can write A dot B or just AB, and we read it A and B is 1. Now that we learned about logic gates, we can talk about flip-flops. Flip-flops are made out of logic gates, and they are absolutely necessary for building a computer. If we put these logic gates in this particular arrangement, we can build a D flip-flop. There are other types of flip-flops as well, like T and JK, but D flip-flops are more common and easier to work with. A D flip-flop has 2 inputs, D and clock, and also 2 outputs, Q and not Q. That little bar over the Q means it's opposite of the Q, which we usually don't use, so we can forget about it. This is the symbol for the D flip-flop. D flip-flop has very interesting properties. It basically is a memory unit. It is like a drawer. You can open it up and put a 1 into it, or open it up and replace that 1 with 0. Any 0 or 1 that you put in it will stay there. How do we actually open a D flip-flop? That's where the clock input comes in. We keep the clock input at 0, and when we want to open the flip-flop, we set it to 1. This is called a rising edge. When the flip-flop sees this sudden transition from 0 to 1, it will be open and will accept whatever signal that is on the D input at that time and will set its output to the same signal. In this example, the output of flip-flop is 0, so there is already 0 inside it. We want to set the flip-flop to 1. First, we set the D input to 1. Notice that this time the output is not changed because the flip-flop is closed. We haven't opened it yet. Then we set the clock input to 1. As soon as the flip-flop sees this transition from 0 to 1, this rising edge, it will be open and it looks to the D input and sees that it is 1 at this moment. So it changes its output to 1. Now 1 is inside the flip-flop. Later we see that both the D input and the clock will return to 0, but the output remains 1. In the next video, I will show you how we can use logic gates and flip-flops to build simple computers that can perform a predetermined task. For now, thank you for watching.